Welcome, everyone. This is Support Vector's meetup session of April the 24th. It's evening, 7 p.m. here in California. And just as a reminder, we used to have the sessions at 6 p.m., but now we have permanently changed the time to 7 p.m. or as permanent as it can be. It is possible that if winter comes and it starts getting dark sooner, we might revise our time. At least for the next few months, we'll keep it to 7 p.m. Now, for those of you who are new to this, again, a very warm welcome to the Support Vectors learning community. We are an AI learning community. Everyone is welcome to this. If you do want to get more engaged, you can reach out. We have the regular paper readings, we have regular tutorials which we give to the public, and a lot of that is free. But we also have much more intense and very serious time commitment requiring workshops and boot camps. And if those interest you, you should reach out to us. Last week, we covered a paper which was iJPEG. The title of the paper was Self-Supervised Learning from Images with a Joint Embedding Predictive Architecture. Now, the title of the paper emphasized two things: self-supervised learning and joint embedding predictive architecture. It is perhaps the first realization of a vision that Jan LeCun had proposed a couple of years ago, a year or so ago, in which he posited that to make machines just bigger, models just bigger, is not the right approach. To just train a machine with rewards, reinforcement learning is not enough. We need to create machines that have some semblance of how biological systems learn. It doesn't mean that it can completely mimic that, but at least it is high time that we make at least some small steps in that direction. And that vision obviously, whenever you have a vision, there is a lot of lack of clarity, a lot of things that are abstract, and is feasibility may be questioned, or you may think, is it even possible to do things like that? Now, this paper, iJPEG, did gain a lot of attention. It proposes an architecture called iJPEG, and it is usually called the iJPEG paper. JEPA stands for Joint Embedding Predictive Architecture, and I is for image. Its twin is the vJPA paper, which is pretty much extending the idea in a straightforward way to videos. Because it's a straightforward extension to videos, I will perhaps cover it a bit later, as it is of practical value, but perhaps not so much to the understanding the foundational ideas that has been proposed. So today, what I would like to do is just quickly review what we did in the iJPA paper and what its core architecture was, and what are the takeaways, and then put it in the broader context of the vision. So in iJPA, one of the remarkable results was, as shown in the first figure, that you could take only 1% of the ImageNet data, which is a massive data set of images, labeled data sets, and you could train a machine to do a few tasks, downstream tasks, without using the iJPA architecture, and achieve fairly high degree of accuracy. And and again, I'm painting it in broad strokes. Now, the core way of doing it is, it does all the learning in the latent space. So you had in the joint embedding predictive architecture, you would take the input, you would pass it through an encoder, and once you have passed it through an encoder, it would go into a predictor, except that you also feed in a latent representation. The idea of a latent signal, a latent variable kicking in, is significant actually. Then the predictor uses the latent understanding that it has, or representation, samples of that, and then takes the encoder, the encoded representation of the input, and makes a prediction, not of the response, not of the ground truth when you're training the machine, for example, but of the latent representation of the ground truth. So in other words, the ground truth too has to be passed through an encoder, and what you get are two latent representations. Now, you would say, well, that's interesting that it worked. And empirically, you see that it does work quite well. But what is it to do with like, how did we come upon this kind of architecture, and what motivates the design of this? So in other words, this architecture wasn't come upon just by hacking and a serendipitous exploration of wiring and rewiring the neural networks to see what works. It was a very deliberate thought process that took the researchers to this particular architecture. And in many ways, this architecture, we may consider this IJPER paper and its success, one can consider to be perhaps the beginning of a much longer journey that is envisaged by the original researchers. So if you recall, and I'm just sort of going through the pictures, what we are saying is that, and it makes a pretty good thing that we are not using contrastive learning. We will be using a different approach without using contrastive learning, without using a generative model, and things like that. In IJPER, you can take an image and you can basically, in very rough terms, break it up into semantic blocks. This is the tail, this is the face, part of the face, or the eyes, and this and that. And then the way to train that is to take a context block that is sufficiently informative, from which one can infer you're looking at a cat, that a human being perhaps would infer. Okay, it's a cat. And then ask the machine, what is it that you would put behind the cat? So in the hope that it should soon figure out that you put a tail behind a cat. So things like that. Or that if you show half a face as part of the context, then what is it that you would ask the target block that you would ask it to predict would be the rest of the face. So when you're thinking like that, you're thinking at a more semantic level. You're training a machine to reason and think, hopefully. Well, reason is a strong word, but we'll use it in a very loose sense, that in some sense reason or about the world, or have a sort of a world model that is in terms of semantic blocks. So that was the main thing. You would take a context, you would encode it, you would take image target blocks, encode it, and then what would you do? You would ground this thing with the location, the coordinates, the position of the target blocks that you ask it to predict. And from there, you would look at the three different predictions for the three different blocks, for example, here. And then you would use a simple loss function, which they call D. And we'll talk a little bit more about that simple loss function. In this paper, they mention the fact that the loss is simply written as the Euclidean or the L2 deviation of the predicted vector from in the latent space from the encoding of the ground truth, right? Ground truth encoded vector, and it is simple Euclidean distance in what they do. Now, it turns out that the formalism that they use is part of a much bigger picture. And let us go, therefore, to the paper that I said I would like to cover. One reason I've done the IJPER because of its very straight, because of its complete simplicity, a very good idea, and a simple realization of a much larger vision. So this is that vision paper that Jan LeCun wrote in 2022. It's been a while now. And we'll go over this paper in some depth. So that is the scope for today. Now, it is a somewhat longish paper, and this longish paper also needs a little bit of a background reformulation of thinking. Not many people are familiar with the concepts like energy model. What is an energy-based models, or interpreting um, machine learning or deep learning neural networks from the perspective of some ideas that are coming from theoretical physics, like, for example, um, Boltzmann distributions with free energy, and so on and so forth. So I'll try to give a little bit of a background, but since we are time bound to finish in an hour or at most, let's say 90 minutes, and it's a pretty long paper, I will be brief. Many of you have expressed interest to learn about a more physics-based approach to deep learning. As I mentioned, and do completely free summer school that you can, if it interests you, you can register for. It would be a bunch of evening sessions during the summer months. But with that thing there, I would like to just explain just a little bit of a thing that we need to know to understand this paper. So, or maybe we don't even need that, but I suppose I would like to bring a very quick, um, basic concepts of energy-based models. And for those of you who are familiar with it, uh, my picture may look overtly and perhaps unfairly oversimplified. For people who are not familiar with energy models, on the other hand, it might look overtly theoretical or mathematical, and I apologize to both these audiences. Right? There is it's a topic that's big enough, and one can hardly do reasonable justice in a few minutes. But here is what it is. See, the basic premise in energy-based models, and but first of all, what is energy? So think of it like that. Suppose you have a system, lots of large ensemble. Ensemble basically means a crowd of particles. Right? So let's say that they have, and this is the classic setting people give. Imagine that you have a tub of water, and the tub of water is at a given temperature T, like a fixed temperature T. Right? And you have a system in which you're looking at lots and lots of particles. So each of these particles will have a certain, given its variable, a certain, should we say, state. Each particle, xi, will have a certain state. And uh, it will have a certain energy, but the average energy of this ensemble, you do know what it will be. It is modulated by this temperature, the heat bath. You cannot have more energy or temperature. Energy will manifest itself as temperature. For example, kinetic energy, these are just molecules bouncing around. But then it has to be in equilibrium with the outside, with the bath, which is common sense. If you put a pot of cold water in a pan, in a pot, and then you put it in a bath of hot water, gradually, and imagine that the tub of hot water is sufficiently large that its temperature cannot be changed, then your pot of cold water will gradually rise up to the temperature, and it will acquire the same energy density as that of as the tub. It sort of makes sense. So now comes a interesting question. Let us say that this machine can be in any one of the internal states, and I would just use the word very vaguely. What it means is that, let's say that here's an atom. It could be not all the atoms or molecules would be in exactly the same state or same energy or the same velocity. Let's say velocity or whatever it is, momentum, whatever it is. Well, I wouldn't use the word momentum because I'm using P for probability, but it's the same velocity. You know that they'll bounce against each other, slow down, the ricochet, and so on and so forth. They will get attracted to another molecule. there'll be forces of attraction and repulsion and blah, blah, blah. So what will happen is that they will show a small variation of states. And so the state that they will be in, there will be some distribution, approximate a probability distribution that you can associate for the state of the particles. Now, what can you do? If you say that if this is the probability distribution, then what state will they be in? People use the concept of disorder or entropy. Entropy is a measure of disorder, right? Or conversely, a low entropy is a measure of how much order or information there is in systems. In information theory, in our world, we often use entropy to quantify information, but actually with a negative sign and all of that. So it's the same thing. Now, one thing is for sure, if any one particle is in a state xi, its energy state is this, it is in this state, whatever position, velocity, whatever it is, you can write an energy function for that. Then you would agree that on average, the energy of the entire system should be, if this is the energy of a particle, let's say, then you would say that there are different proportions of particles at different energy states. So what you would say that the expectation value of the energy, the average energy, which is sort of controlled by this temperature here, this has to be exactly, the probability distribution has to be such that whether you can write it as a summation or an integral, but in the beginning, let's say that you have lots and lots of molecules. By lots, I really mean a lot. Just to remind you, we are talking about numbers this big, which are frankly ridiculously large numbers. And we can say that if you do this, the probability density, the expected value of energy has to be bounded. But you can have this average energy by having, let us say, you could still have that by having all sorts of probability distribution, weird things, some particles being highly energetic, some being not energetic at all, and so on and so forth. So the constraint that is often used, it is called the Jane's maximum. I'll just write it because this is now getting a little bit far afield, but I'll just mention it because it leads to one of the most celebrated things that we use in machine learning. Entropy principle. What it says is that left to itself at equilibrium, left to itself at equilibrium, an ensemble. So in our case, an ensemble is literally all of those molecules in the liquid forming or gas, that is your ensemble. An ensemble will achieve a state of maximum disorder. In other words, there is no reason for any order to remain. Maximum disorder. In other words, maximum entropy. Right? This is very easy to illustrate. Suppose I take a beaker with water and you put a nice solid drop of ink. Well, might as well make ink a different color. Let's say you put a very nice drink. Now you realize that the system is highly ordered. Clear water. This is clear water. All the ink is in one place. So it's a highly ordered system. And as you know, over time, as it achieves equilibrium, you will go through states. So this is let's say that your initial state. Then you will go from here to a state in which this begins to diffuse, the next state, and it will go to another state, and eventually you will reach a state in which the water and the ink will be indistinguishable, isn't it? So they will achieve a state of maximum entropy, these molecules left to itself, right? And this would be your equilibrium state. This is a common sense experience. Equilibrium. Okay, I'm being terrible about it. Equilibrium. All the molecules would have, the ink molecules would have uniformly, more or less spread throughout the water. That would be the state that maximizes entropy. So what you are saying is that equilibrium states would be achieved when you would achieve that state when the entropy, max entropy. Entropy, by the way, is given by minus a p of a particle xi log p xi. And this is something that I suppose we are all more or less familiar with. If you're not, think of it like that. Entropy is a measure of like how, what's the average surprise in some sense that the system gives you. And what you're basically saying is that the more negative it is, the less surprised you are. So when ink completely dissolves in the water, you would agree that the least surprising outcome you would expect. At that moment, there's total disorder here. Right? And so this is it. And obviously, these equations convert into integrals. Like if you want to look at it in terms of so deliberately, I was being fuzzy about little p and capital P because in the continuous case of infinite number of particles, etc., each of these integrals would change to sigmas. Summations would turn into integrals, and capital P would become little p, probability densities. That's a thing. But the point is, why am I bringing this up? The reason I'm bringing this up is if you just agree that systems do tend to behave this way, it turns out that very soon you can prove to yourself that if this is true, then the equation for the probability of a particle, of a state, of any given state is given by this expression, e to the minus e. So of a particle or a system being in the state x, right, divided by t and followed by z. This is called the partition function. The partition function. Now, what in the world is this? Basically, what it is saying is this statement, and it's something like this, you keep seeing it all over the place. Now, if you look at it very carefully, those of you who are familiar with the softmax function, does it to you look uncannily like the softmax function? Isn't it? So I'll give you a little bit of a aside here. If you think of a softmax, when you do a classification, what do you get? You have a neural network that produces logits, hidden states, H1. Suppose you are doing a classification between H3, H4, H5, the 5 possible outcomes. Those numbers that you come from a neural network, so you have a neural net, it produces these hidden state representation. And now the question is it a cat, dog, horse, zebra, duck? What is it? Now what happens is these things, these are usually called the logits, or people often call it the latents. Yeah. You need to convert it into probabilities. You need to convert these into probabilities. And to convert these into probabilities, what you do is you do e to the hi. The probability of a state ith state is this. A probability given probability of yi given x is this, divided by summation of over all possible states j. So this is your softmax. I hope this sounds very familiar to all of you. And now you see the analogy of this, or a complete thing to this. This is exactly what Z is. Z is essentially, in the case of a discrete situation, it would be e to the minus ex I, let us say, over t, summed over all of the possible states. So in other words, you realize that it is in a way a normalizing factor. We typically in softmax just think of it as a normalizing factor. Though it turns out that if you look at it from an energy model, actually Z, its real name is the partition function. And for reasons that we won't go into, it is actually the star of the show. There's a lot there in the partition function, but we will leave that. And of course, in the integral form, it becomes this. Right? It will become like e to the minus e to the x over t over all the possible states, that x can acquire, all possible states of x. Does that make sense for you? So now let us just recap. You say that the probability that the system is in state x is given by e to the minus energy of that state divided by t up to, let me just put it as a proportionality factor. Then we can skip the z, which is a constant partition function we have taken out of the equation for a moment. And just for a moment, we will ponder over it. What is it trying to say? What it is trying to say are quite a few things. It says that if energy Ex is low, probability is high. Would you agree? Small values, for example, if Ex is equal to 0, then P of x is proportional to basically 1. Right? 1 over z. It becomes basically 1 over z, the partition function. And very specifically e to the minus x over t by z. So you realize that if energy of a system is 0, then the probability of that is just 1 over z. On the other hand, if E of x is, let's say, something like this, very high energy point, the probability that the system is in that state of that is close to 0. Now, this is the point that we need to, this is the point where energy, this theory or the statistical mechanics and thinking in terms of energy meets machine learning and this energy-based models are born. What the fundamental hypothesis, I suppose, or the premise of energy-based models is, given a system, so suppose you have a system, X is your input, you have a box, and you send it through your neural network, some sort of a model, and it produces a Y. Right? Y hat is your prediction. Now, let us say that this machine, this neural network, discovers, let us say, the neural network discovers an energy function, and I'm using the word energy in a way, by studying the data, and again, I'm using colloquial words, studying the data. What is the data? It will be XY, a data, label data, XY data, let's say. By studying the data such that energy of X and real Y, some actual instance of energies, actual data points would be low, but energy of Xi and some not likely outcome. Let's say that this is cow. And in reality, these are the parameters, these really were about cow. And Xi, let's say that this is again about cow, but the energy function would predict a much higher value if your Yi, if you put not a cow, but you put, let's say, a duck. Right? And what it is basically saying is, it is a joint function of input and output. And what this function does is it's an energy function that says that states which are unlikely, so let me state the main premise, the states, energy of states that are unrealistic. Right? So, for example, imagine a big animal, 200 pounds, big size, And then you're looking at the energy function of it as input, those measurements as input, and the and duck. And what it will say is that energy of the state is that are unlikely is high. Conversely, energy of states that are likely, like for example, a big animal, big tall animal, is likely to be a cow. The label, the most likely label for that is cow as opposed to a duck. So you say the energy of states that are likely will be low. Now, the way energy models look at it, or the way reformulation in terms of energy, is that the task of a machine learning model is to learn the task is, the learning task is to learn this energy function, E, X, Y. Are we making sense? That is it. This is, you reformulate it like that. Now, in practice, what happens is discovering this energy function in many cases is very close to basically doing your traditional loss function. Though energy function is in some sense more general. It turns out that energy minimization, how would you learn the energy function? Through gradient descent. This is the one trick we have for everything, a gradient descent. While training, often it looks like the loss function, or is related to the loss function that we are familiar with, mean squared error loss, negative log likelihood loss, or at least you can relate it to that. On the other hand, the main point of energy function is that you can use it at inference time. It's not something, loss functions you don't use at inference time to discover optimal solutions or predictions. And that is a key point actually about the energy based models, that they could be used. You could do gradient descent by using, and this point needs a little bit of a thinking through, because it's at the crux of what some of these things that we are going to talk about is here. That if you have an energy model and an energy function, you could use the energy function once the model is trained and you're in production or you're in inference time, you could still use it to search for the optimal solution. Right? So the idea is that the training will take you, let's say, to an energy function that is like this. It is basically saying that these things are more likely. If this is the energy function associated with some state, these are more likely, and you could essentially sample off this, and then you could use a form of resampling or moving forward and converging onto. So suppose you start with some value, and you could at inference time still gravitate to the optimal solution through gradient descent or through some process or sampling or something like that. But so long as you know the energy function. And that is sort of one of the key things that people in the energy model keep talking about. So with that background, and you will see, sometimes you will keep asking, hey, energy function, isn't it just synonymous with loss function? Well, the answer to that is yes and no. In certain circumstances, they become effectively similar, but that's not the way to think about it. And they have energy models and energy functions have a much wider sort of a perspective, a look, and they can be used at inference time too. It's a point that is worth bearing in mind. So with that, let's go now, with that background, let's go now and read this paper. It's a very important thought paper. Now, one may agree or disagree, but the fact that there's downstream research that has succeeded, that is producing results, I suppose, is a testament that there must be some really good merit to this, thought paper. Right? Now, be warned that this is unlike a traditional paper, which is the traditional paper will have IMRC, Introduction Method Results Conclusion. So you'll introduce what is it that you're going to do. You'll show related work, prior work other people have done. Then you'll give your method as a new novelty. Then you'll show that the results have come out quite good with those methods. You'll beat the state of the art. And then you'll conclude. That's a typical thing. So IGPA paper is along that line. But this paper is slightly different. And this format itself is different. It's a long paper, long read, a very interesting read. And it is far more English and thinking than technical jargon at all. So let's read this paper. So today's session might be a little bit longer session for that reason. Abstract. How could machines learn as effectively as human beings? How could machines learn to reason and plan? How could machines learn representations of percepts and action plans at multiple levels of abstraction, enabling them to reason, predict, and plan at multiple time phases? This position paper proposes an architecture and training paradigm with which to construct autonomous intelligent agents. It combines concepts such as configurable predictive world models, behavior driven through intrinsic motivation, and hierarchical joint embedding architectures trained with self-supervised learning. Now, as you read through this, you can see the grand vision. This was written in 2022. Already by then, people's mentality was that bigger models are better. Let's do a lot more training, a lot more reinforcement learning, rewarding punishment, things like that. Those were the ruling paradigms. But if you really look at artificial intelligence, you do know that machines are not really intelligent at all. They do create some semblance of special ability to do specialized things that is a simulacra of intelligence, but we don't have intelligence. So, and to the extent that Jan LeCun is one of the pioneers and a Turing Award winner, obviously the long-term vision of people like Jan, researchers like that, has been to generally make machines intelligent, to make them think and reason and plan and so on and so forth. At the end, and we have to not forget that our entire field started, even in a practical way, with Charles Babbage not trying to make a fancy calculator, but trying to make an intelligent machine. Alan Turing, he was trying to, in practice, crack the Enigma code, but in reality, he was trying to do it using a universal machine and some form of artificial intelligence, some form of a thinking machine that could crack it, and so forth. So while those dreams have forever remained out of reach, it is, I suppose, quite remarkable what enormous ideas and progress has come in the pursuit of those dreams. I would classify this paper, time will tell how much of this paper will be realized as reality. It's a very aspirational paper. It even goes on to talk about machines, emotions. It even goes on to say, and something that one would be skeptical of, certainly I am, that using this approach you can create emotional machines. I don't think so. But the fact that these great minds aspire to such things certainly, I hope, will lead to great discoveries as this program is pursued. So this is starting a research program in many ways. So, for example, how could machines learn as effectively as human beings? And what is the problem with that? Human beings and animals and living creatures, biological systems, we learn from far less data. We have evidence that children can pick up, small babies can pick up addition. If they're not born with, there's even evidence that we are born with the ability to do arithmetic up to 10. But even if we are not, in a very incipient stage of our development, we do pick that up. Whereas the only data we have is staring, I suppose, at our family and the few objects within our field of vision and sound and perception. So not as much data as these machines need, which need trillions of tokens to be trained. So these are efficient machines. Animals and human beings well, I suppose human beings are animals too, but I'll just use the word biological systems, have a far more efficient way of learning. How could machines learn to reason and plan? It's one of the pursuits. Can you make machines reason and plan? And you'll see that it proposes an architecture to do that. How could machine learn representations of percepts and actions? So this is about representation learning, and as coming from the previous paper, you know that a lot of it is about learning things in a joint embedding space and things like that. When it talks about multiple levels of abstraction, by now we are thinking hierarchical JEPA, the same JEPA that we dealt with algebra, but in a more hierarchical way. I'm just putting more color to it right up front so that as we make our way through the paper, it becomes easier to read. Then it gets much more practical in the next sentence after the questions. This position paper proposes an architecture and training paradigm with which to construct autonomous intelligent agents. So iJPA was sort of a first step in that direction. It combines, etc. The rest of it, but the important thing is we encountered a joint embedding architecture trained with self-supervised learning. We have seen that that was true. We didn't see the hierarchical part of it, and that, I suppose, is work or research papers on that are yet to come in due course of time. They will come. This program of research is in its early stage. Now, this is a paper that is, again, whether you like it or not, it depends a lot upon whether you want very concrete details and specific, how do I do that, or whether you're fine with thought papers and position papers. It is written with as little jargon as possible, but the operative word is as little. It is not free of jargon. There is still some jargon. And it does need a little bit of a prior knowledge, but I hope I've already given you that. So now, let us, I won't read the whole paper that way. But the first paragraph, first couple of paragraphs are worth it, and I'll very quickly read it. Animals and human beings exhibit learning. I mean, the bias is very obvious, actually. I suppose if you come from the Eastern world, you would consider it is somewhat superfluous to say animals and human beings. Animals would be enough. We too are animals, but I suppose it's a very heliocentric point of view to distinguish between the two. We take it as this. Exhibit learning abilities and understanding of the world that are far beyond the capabilities of current AI and machine learning systems. How is it possible for an adolescent to learn to drive a car in about 20 hours of practice, and for children to learn languages with what amount to small exposure? How is it that human beings will know how to act in many situations they have never encountered? By contrast, to be reliable, current ML systems need to be trained with very large amounts of trials so that even the rarest combination of situations will be encountered frequently during training. So this is the way, the state of the art of training today. Still, our best ML systems are still very far from matching human reliability in the real world tasks, such as driving, even after being fed with enormous amounts of supervisory data from human experts after going through millions of reinforcement learning, trials in virtual environments, blah, 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 blah. So if you think about it, it's a given thing. He has latched onto the fact of driving. Driving is a poster child of where AI has failed almost miserably. It always seems to be within reach, but just a little bit away, self-driven cars or autonomous driving. Kids do it in no time. I'm told that some car company, I think Tesla or something, even started taking down payments for cars that with the self-driving feature, and people paid for it. And it took them many years to realize that it's one of those things, like I suppose fusion, that looks easier in theory than in practice. And so, to the best of my knowledge, there are no truly autonomous self-driven cars at this moment, or likely to be in the near future. So it speaks to that. Still, our best ML efforts are very okay. I won't go into that. It goes on to say the answer may lie in the ability of humans and many animals to learn world models, and therefore we introduce one of the core concepts we'll talk about. This paper will talk about, and I'll just key it in and repeat it. World models. It claims that human beings create a sort of a internal representation or a world model, and they respond, they act from that. So when inputs come in, it is always contextualized with the world model to determine what the appropriate response should be. So, and this has, I suppose, many representations. For example, in basic things, when you and I talk, very soon we have a so-called theory of the mind. We have a world model of what you are thinking. Part of the world model is we have a pretty good idea of what you're thinking, so that when we talk in reference to what you think you understand so far and are thinking. So that's happening everywhere. Before we cross the road, we have a world model that says that even though we don't see the car, there might be a car coming very fast. Let's cross the road quickly. Things like that. That's world model. There are three main challenges that AI research must address today. How can machines learn to represent the world, learn to predict, learn to act largely by observing? And this word is learn to act and largely by observation. I can't emphasize this thing enough, that what we are saying is learn everything, learn largely by observation. To predict, learn, etc. is the superfluous. The more important keyword here is learn largely by observation. And it is saying you're not being told this is a cow, this is a duck, or this is this. But can you, in a sort of a self-supervised way, learn it? Many people have called it, in some sense, the problem that our current machines don't do that very much. Autoencoders, in some sense, do that. There's some instances, but broadly speaking, the world is about supervised learning rather than self-supervised learning. Interactions in the real world are expensive and dangerous. Intelligent agents should learn as much as they can about the world without interactions. So the interactions are expensive part is easy. It takes a lot of data, right, to train it. And dangerous sometimes. For example, there is no data that you can really create to easily train a machine in some completely unknown and dangerous situations. You wouldn't know. Unpredictable and dangerous situations. How would you do that? How can machines reason and plan in ways that are compatible with gradient-based learning? Now, this speaks to that. The core thing, why is the statement relevant? It goes to the fact that a gradient, we have only one tool. Learning is gradient descent. The only method of learning that we know is gradient-based. Now, when I say gradient-based learning, by the way, one may, if you're more mathematically sort of savvy, you may jump up and say, hey, gradient-based learning is only a first-order learning. I can do second-order learning, third, and so on and so forth. I could bring in the Hessian and second-order methods and whatnot. Yeah? I suppose when the researcher here means gradient-based learning, it means any of the derivatives, first, second, third, fourth, whatever you want to take. Right? Well, nobody goes to third, but there's a first and second order. Using the term in a more gentle way.
It seems to be once we become much deeper had much deeper neural networks, like Newtonian methods that take advantage of second order information, just don't seem to work nearly as well. We gain a lot of information, but it's just expensive.
It's expensive. But yeah, no, your point is very correct. See, with second order methods, there have been a whole slew of objections. People have said that computationally they are more brutal. Secondly, in some sense, they converge very fast, too fast. And there is a general belief that slow learning is better learning. You're more likely in a non-convex loss landscape to converge to the right solution, a more optimal solution through a more slower learning process. That's why, all the rate schedulers and all of that. Having said that, second order terms have always been, sneaking around the periphery. If you look at the Adam optimizers, they do have a second order term. It's just gradient squares and things like that. There's a little bit of that always around the periphery somewhere, optimizing on the first order methods. So yes, but your point is definitely true. There are people who sort of are unhappy that we don't use second order methods. And there's no real fundamental reason they shouldn't work. But in practice, yes, you're right. They don't work. So the third is, how can machines learn to represent percepts and actions planned in a hierarchical manner? And this point, obviously, I keep telling people a joke that, see, if you go to watch a play, as in real play on a stage, and if you notice that in the stage, there is let's say simulation of a living room, and on the wall there is a gun or a sword, you can bet that somewhere later in the story, that gun or sword will be used. It has a role in that story. So I always am, watch out when people are sort of laying the stage for the rest of the paper. In the introduction, they're laying the stage for the rest of the paper to watch out for keywords. And here the keywords to watch out is hierarchical manner. And I'll just sort of pencil that in at multiple levels of abstraction. So as you can imagine, this paper is going to propose something that will help us do hierarchical learning. Now, it goes on to say, and obviously I'm deliberately going slow, I apologize. The present piece proposes an architecture for intelligent agents with possible solutions to all three challenges. It says that it proposes a possible solution to all three challenges. It's a bit more tentative, and I suppose a muted way of stating it. Later on in the paper, the author tends to be far more insistent that he has come upon some really good ideas, and there are reasons to believe that certainly the ideas are very fertile, whether or not it does fully address the things that he was hoping it does. The three main contributions of this paper are the following: an overall cognitive architecture in which all modules are differentiable and many of them trainable. Why is it a cognitive architecture? It means a learning architecture. Let's give that. Why is the word differentiable here important? It again goes back to the fact that we can only do gradient-based learning. That's all we know. If you have a fully differentiable system, what does it mean? You can do gradient descent, backpropagation. All of the machinery of a neural network is there. So if you take what he's saying is that you can create an architecture which preserves differentiability end to end. JEPA and hierarchical JEPA. JEPA obviously standing for joint embedding, right? Predictive architecture, and hierarchical as well. And the point that he makes over and over again, and is crucial, it says it's a non-generative architecture. Now, think about it this way. If you remember the iJEPA paper, for in-painting, it was for just predicting what was there at the tail end of, at the end of the cat. The machine could say, well, I can predict that it is a latent representation of a tail. Right? And then, of course, you could use some sort of a diffusion model or something from that to generate a tail and put it to the cat. But the point is, this architecture itself is silent. It just produces. It's non-generative. And at some point in some talk, the author does go out to point out that the problems that you have with generative things is pixel-wise generation is, he puts it quite bluntly, it says it's dumb. The machine is not learning it. It is just using clever tricks to infer probabilistically the values, which is one reason, I suppose. Many people point out that it is so hard for all these generative models to draw human fingers. Like whenever you you ask it to generate a human hand, it tends to have quite a bit of difficulty with the fingers. Now, those things are getting improved upon. Everything evolves. The things can be fixed in two ways: with a radically new idea or with evolutionary fixing. So both those journeys are happening. In some sense, the new diffusion models are pretty good even with the hand. They're getting better. And the other side is, in contrast, there are ideas like this paper suggests, which is to say, let's rethink the whole thing and do it differently. So that is it. A JEPA architecture, a non-contrastive, and that is another big thing this paper makes a big deal out of. It says that it's a non-contrastive, self-supervised learning paradigm that packs a huge punch. So let's break it up into its constituent pieces. When you look at, for example, you train, or where do we use contraster? If you think about it, the semantic search, underline, RAG, etc. A semantic search is trained using, if you go back to the original sentence word paper, it uses a contrastive loss. How do you embed sentences into a latent space? What you do is you take a sentence, a reference sentence, you take, let's say that you take a sentence X of text. You take a very similar sentence, similar, and then you take something random. With the presumption that in general or statistically, random will have nothing whatsoever to do with X. And then contrastive learning basically says, and we went over this, minimize the distance, you minimize the loss. Right? Basically, X will land here, make sure that S lands here and R lands here. So if you have, or let's put it this way, let's say that in the beginning, X lands here, S lands here, and R lands here, randomly. And then the whole learning process or the contrastive loss will make these two come towards each other, and these two go away from each other. X and R should move as far away as possible from each other. And so you should eventually reach a state, a happier state, in which, let's say, the new state will be X, S, and R is far away. Right? These vectors, well, not the X, I should say, the latent representation, Z of X, so I apologize. I shouldn't have said X, I should have said the latent representations of X. Latent representation X, ZS, ZR, and ZS, ZR. You want to make the latent representations of similar sentences come together and of a random sentence to be far away from its latent representation in the latent space. So that's an example of contrastive learning. Once you get this idea, then it is a no-brainer to write a loss function. Basically, it will be minimize distance between X and S and the negative of the distance between X and maximize the distance between X and R, which is the same as minimizing the negative of the distance. That's one way to write the contrastive loss. Right? It is always based on triplets, or people often call it the triplet loss. So that is the contrastive loss. Now, what is the problem with contrastive loss? The problem with contrastive loss, amongst the many problems, contrastive loss has been there, and it is very, very effective. Today you do your semantic embedding, a lot of that, sentence encoding, etc. Using semantic loss, you clip the same idea when you apply to images. It becomes the clip, the first powerful multimodal model that came about. If you remember, contrastive loss image pre-training. You take an image, you take a caption, and then you take some random caption and you train the contrastive loss, and you get clip. Right? And so we entered a world in which you could search for an image using text, and you could search for a text using image, and so on and so forth. Remarkable progress has been made with contrastive learning. But there's a problem with contrastive learning. The problem is the curse of dimensionality. See, let's say that the dimensionality of this latent representation is, and these days you notice that it is getting higher and higher. If you go to the Hugging Face leaderboard, you'll often see dimensionality like this, 1024 or something vast, or even twice that, 2048 dimensionality. These are vast dimension spaces. You realize that when I'm doing the training of the model, and I'm trying to bring ZX and ZS close together, I can do a gradient. I'm doing a gradient at that moment. And there's so many directions. So for example, in two dimensions, from this point, I can move here, limited. The moment it goes to 3 dimensions, now I have far more ways or directions that I can move. And then there's even more dimensions, and even more directions that you have to search for. Where do I go to minimize the loss? Right? And so contrastive loss functions, they tend to suffer from the curse of dimensionality, amongst other things, nality. But it's a very powerful classical method. But he makes it the author makes an important point that the architecture he's proposing will not be using a contrastive loss. It's a non-contrastive. The other thing is self-supervised learning for practical and ideological reasons. Practical reasons, creating tons of label data is prohibitively expensive. Right? You can't create trillions of points of label data. All systems use some trick. For example, when you train BERT, what do? We use mass language model. What does it mean? You take a sentence, the cow jumped over the moon, and then you basically go and hide the word cow, and then you ask, okay, what jumped over the moon? And then cow becomes, so the mass sentence becomes X, Y is equal to cow. Cow becomes a prediction. So you, in a way, create supervised data by taking not a very practical, but a useful technique, mass language model that produce a lot of training data. You train the model, then therefore to predict the mass flow. So there's always a trick when you're dealing with training a massive language model, because you can't, frankly, create supervised or labeled data. So that's that. So, but then the point that Jan is making is that human beings don't need to be like, for you to learn what something is, there is never a labeling, implicit or by tricks or by anything. It's a very passive form of learning. And he identifies that in machine learning, the closest thing to that is supervised learning, a self-supervised learning paradigm. An example of a self-supervised learning, that is, obviously, the moment you talk of self-supervised, people often begin to think in terms of, for example, an encoder-decoder. Example, when you take a typical autoencoder, what happens? You feed it X, and X prime comes up. Here is a latent representation, and you want X prime to be approximately the same as X. Do I hear a question? Okay, so X prime, you want it to be more or less the same as X, and by forcing it,
if you're writing, we can't see it on the Zoom.
Oh, you can't see that. Is my screen not shared?
It's shared, but I think if you started writing just now,
I'm writing in the extreme left-hand corner. So let me write it in a bigger way. Okay. So let's say that you this. Are you seeing my writing now?
Yes, indeed. Yes.
Let's say that you feed in X, an image, which is the picture of a cat. And what do you expect? You want an autoencoder to produce essentially a picture of it, the simplest vanilla form of autoencoder, even though you have forced it to learn a lower dimensional latent representation Z. Okay. You have an encoder function of X, and you have a decoder function of Z. You expect it to be able to, so you want to say X prime that comes out, X prime, it must be the same as X, to the first approximation. And the loss function, therefore, is just this, the gap between this. Let's say that you can treat it as, in the regression case, in the case of images, you just do pixel-wise loss, the Euclidean loss, or the Elton loss. And we could do that. But so this is a basic example of self-supervised learning, because then what happens? You can learn this representation, Z, without reference to any label data at all. So something like that. So now comes the points that so now that explains the third point, which is quite crucial. I suppose these are the three main points he's trying to make. A non-contrasted, self-supervised learning paradigm that produces representations that are simultaneously informative and predictive. And here, I suppose, it's a dig at purely generative models, which are non-informative, which just are pure predictive. Hey, I can in-paint what was missing in this image, right? But what exactly is the inner representation that helped you do that? Well, there wasn't. That's the problem. Or there's not at least interpretable version. The fourth point it makes is a way to use HJPA. What does H stand for? H is the hierarchical. As the basis of predictive world models for hierarchical planning and uncertainty. Now, this point is a contribution whose meaning will become more obvious as we make our way through the paper. I notice that we are already an hour into it, so it seems that we should be covering this paper in 2 settings, but let's see how far we can go today. I suppose I need to move a little bit faster at this moment. If you look at this chart belongs to, I suppose, a neuroscientist or a cognitive scientist, which says that this is, to the best of our knowledge, this is how babies learn. This axis is the months. And if you notice that babies, they pick up emotions and imitation, etc. Early on, face tracking is an action that comes very early on. But the fact that objects actually don't disappear, they don't teleport. Your mom is standing there and then suddenly disappears or teleports back into place. That doesn't happen. That realization does come pretty early on. That things have a permanence to them. They have a solidity and rigidity. Natural kinds of categories, this is that moves, this stays fixed, the wall doesn't move, people move, and things like that, biological motions, etc. You learn these things and build upon it. So, for example, shape constancy, these things gradually come and they sort of build upon each other. That's the point that you're making. So, as all with paper, usually it's worth reading the caption of the figures because they are very informative. So we'll read that. This chart, courtesy of Emmanuel Dupont, indicates at what age infants generally acquire various concepts about how the world works. It is consistent with the idea that abstract concepts, such as the fact that objects are subject to gravity and inertia, are acquired on top of less abstract concepts, like object permanence and the assignment of objects to broad categories. So let's make little arrows to illustrate the point. He says that this fact depends upon these 2 facts. You couldn't come up with the idea of gravity, inertia, and conservation of momentum, that things in motion stay in motion, etc., unless you realize that objects are there, they have some certain solidity and rigidity. So that's what the author is trying to say. I don't know if necessarily I would literally agree to such a linear sequencing of learning, but there's something plausible about it. Let's leave it at that. Now comes a very interesting picture. It's sort of a very, what he says is that you can think of the world, he says that human beings or a system for autonomous intelligence should look like this. There is the world, something happens in the world. He has painted the whole world with a big earth. I would literally have put a bouncing ball there. So imagine there's a ball bouncing and coming towards you. So that to me, that's how I explain it to myself. Then you would have a perception of that. Your brain would have a perception of that. The brain may then ask the actor to do something. Well, if you are a kid, your first response would be to run towards the ball or to evade the ball if it is coming straight for your nose or face, or whatever it is. That is decided by the actor, and that would be a kid. But at the same time, your perception feeds into a world model. You see it's a ball bouncing, it's coming towards you. You have a world model, amongst other things, that says it's safe, you don't need to run from it, it's fun, you need to go have fun with it, things like that. So that is your world model about what's happening. And then it has, you also have short-term memory, because you remember the ball was here or there, if you're playing with it. And then the critiques so these are the things that will come in at some point. The cost. Think of it, cost and he would use the word cost and energy function, etc., somewhat interchangeably. But think of it as somewhat like a reward function or or a way of saying, or the energy. Well, in different contexts, it means different specific things, but we'll leave it as that. It's basically an energy that measures the level of discomfort of the agent. So, for example, if a ball is coming straight at your face, you would say, and if you just stay there and don't do anything, the energy of that particular thing state would be pretty high. It would represent, I suppose, a discomfort. You would startle. You would say, "Oh my God!" Kind of thing. I suppose that's what he means. The short-term memory, I think all of it is there. Obviously, this is not very precise. I mean, none of it can be quantified, and it is very much like a. Doesn't it feel like that? That this is how it works, kind of a thinking. And then at the apex, he has put a configurator, and then let's read through this figure again for details. A system architecture for autonomous intelligence. All modules in this model are assumed to be differentiable. Why? Because gradient descent is all linear. In that, a module feeds into another one through an arrow connecting, etc. The configurator module takes inputs not represented for clarity from all other modules and configures them to perform the task. So your configurator is more like the orchestrator, or think of it as the mind, the perception module estimates the current state of the model, which is okay. So basically what you're saying is, let's say that the input comes here. What the perception module will do is it will encode the input. So perception is sort of an encoder. X goes in, and encoding of X, a Z comes out, a latent representation. Let's say SX comes out. Right? It perceives a certain state of the world. Module predicts. The perception module estimates the current state of the world. So this would be, let's say that X is what it sees. It comes up with SX. The world module predicts possible future world states. So in other words, if this is it, then it has to predict what will be the next. So let me just call it S0. What will be the S1X, the next state? After that, what will happen? So for example, and that's why I use the example of a bouncing ball, because your mind literally can play itself out. It can predict what your world model about a ball. It tells you that this is what it is going to do. But can you imagine that if the ball just stopped bouncing in midair, that would startle you? That would go against the grain of your expectation. The cost module computes a single scalar output energy. So this is where it ties into the energy, the concept of energy that measures the level of discomfort of the agent. It is composed of two subunits: the intrinsic cost, which is immutable, not trainable, and computes the energy of the current state, pain, pleasure, hunger, etc., and the critique, a trainable module that predicts future values of the intrinsic cost. So there's a little bit, I suppose, perhaps overthinking it, or maybe it might not be in exactly this way, I suppose, but it is at least a way of thinking about it. The short term.
Can I ask you a question, Asif, Ravi?
Please.
Yeah. So, I think it looks like the world model here, like maybe sidesteps or ignores the tactile or the multimodal nature of learning for a child, for a bouncing ball. The bouncing ball is touched, it moved around. The child basically doesn't just look at it and learn, right? It actually feels it, moves it, interacts with the data, and then learns, right? It's not, the learning is not just purely vision. It's not just looking at it.
Yes, you're right. The way I look at it is, world model is the belief, the world, this is the objective reality. The world is the world, and it behaves a certain way. It is made up of certain things, and it shows certain behavior. World model, based on, or in a way you can say, it is the conditioning of the mind. It has, through all its interaction with the world, through all this perception and everything that has happened, it is more of a subjective mirroring of the world. It is its perception. Like, so for example, let's say that the only thing, two people, two machines, two kids, one kid, every time a ball comes, and the ball tends to hit the kid. Excuse me. Then, thank you. So to that kid, the world model is balls, the predicted state, this ball will come and hit me. On the other hand, another kid's perception would be the ball will bounce quite a bit and run here and there, and it is fun to go chasing it, right? To go there. But you don't really expect it to bring sort of things that will hurt you and things like that. So that is it. That is the world model. It is your anticipation, your subjective picture the machine has of how the outside reality is. Right? And there's a very close analogy to cognitive science. See, the world is huge, but we perceive it through the limited perception that we allow to come in. And machines are also trained in only the data set that they get. So any world model that they build is necessarily fragmented, is necessarily incomplete, right? And is necessarily conditioned on past training. And that is something that you see develop in this. What the author is going on to say is that world model is the evolving thing. At the end of the training, what you want is a good world model that produces a good cost function or an energy function.
Yeah.
And from that, you can derive the rest of it. So, Nacho, that's the way I would answer this. The short-term memory is just the transactional memory and so forth. And the short-term memory, as it will become in the architecture, is basically the states while you're still determining what you have to. A model architecture. So now it gets a little bit more interesting. And now we also have an inflection point here. I notice that the time has become 8:35. I would like to go on further for half an hour. Perhaps we could revisit and do the rest of it later. This is a very interesting paper. There's a lot being said. So many of you are probably familiar with Kahneman's book, Thinking Fast and Slow. Remarkable book. And so for some of his thoughts, he got the Nobel Prize. But essentially, it creates a model of our human thinking process, cognitive processes. It says that we have what he calls system 1 and system 2 thinking. And in this paper, they call it mode 1, perception action, and mode 2. There are two modes in which you act. And those two are worth mentioning. When we think fast, like if I were to, and he goes on to give an example. The book starts off with an example that later on got hotly debated, but for whatever it is worth, it is worth pointing out. If you were to ask, I don't remember exactly what example he gave, but I think he gave this example. I may be wrong. He said that if in a village, you find a person who is very studious, loves books, or just has a love of books, not studious, just has a love of books. Is she more likely to be a librarian or a farmer? And if you think fast, you say, loves books, librarian. That's more likely. And yet, that is less likely because in a village, a farming village, most people are farmers. Librarians in the whole village will be just one or two. And even there are far more farmers who are likely to, even there's a proportion of farmers who have a love of books. Not all farmers avoid books. And so, if you reason through it, you come to a different conclusion. You would say, well, it's probably a farmer who happens to like books rather than a librarian, because in that village there would be just one librarian. Many people who are farmers who happen to like books. That's the way I remember that. But see, anyway, it points out that this fast thinking mode is a survival mode, and it comes from our conditioning. We reason a lot, and we see that the more we learn about something, for example, when we do calculus, for example, suppose I were to give you an example. Let's say if I were to give you e to the x cosine x squared, a function, and I say, go and differentiate it. The first time around, you would probably do it very piece by piece. You would create all sorts of intermediate variables and things like that, and go about trying to solve it in little pieces. But as your muscle memory, as your experience about it increases, you will notice that you're not creating as many intermediate steps. You quickly can produce the answer. And there's something quite remarkable. There used to be a great mathematician. Actually, since I gave this example, I don't know why this digression comes to me. There was a great mathematician named Ramanujan, who was during colonial India, he was discovered by, of all things, G.H. Hardy, a mathematician of Britain, because Ramanujan sent a crazy letter with lots of interesting mathematical results. And the distinction between the two people was that G.H. Hardy, a leading mathematician of his time, was completely a system 2 thinker. Everything had to be laid down in precise detail, because there are many things that can go wrong when you prove a theorem. So he was a very careful reasoning person. Whereas Ramanujan, to the best of our knowledge, or if you put it scientifically, he leapt to the answer in one leap. And it almost was a Model 1 thinking, except that he was never wrong. His notebooks have almost no errors, but they have no intermediate steps either. He would write mathematical theorems and just state them as facts. And I suppose to him it was dead obvious. To the rest of humanity, 100 years have gone by and we are still trying to prove many of his theorems. So that in some sense, that goes to prove that I suppose in some people, the steps become so obvious that they sort of disappear. And one of the things that this paper points out is that something very similar will happen. As you train a machine to do system 2 thinking, gradually you can condense or distill a lot of that reasoning to automated action. Just as, for example, a cricket player or a sports person in the beginning practices using techniques, but after a little while the techniques become so inbuilt or second nature that it becomes system 1 thinking. So there's a lot of this reference to Daniel Kahneman's work in this paper, but we'll get to it. So let's look into this model. What it is saying is, let's say something happens in the world. And in my case, I wouldn't think of the whole earth. It's too big for me to think through. Consider bouncing ball. And you have an X, you encode it. When you encode it, you have some representation of the world. A ball bouncing. Then there is an actor. What the actor can do is it can basically predict using this. Actor can come up with a state action that you should do. But there is a prediction that if you do this action, what will be the state of the world after that? What will it happen? If you hit the ball, you have some idea and you have some notion, some energy that you associate with that action. So let's say that you see this ball. The first initial state is it's coming towards you, let's say. And then you realize that, oh, what fun. Let's go hit that ball. And then you get to a state that's a bit more pleasure, that's lower energy or something like that. That's it. So let's read this thing here. Mode 1 perception action episode. The perception module estimates the state of the world as 0 is nth as. The actor directly computes an action or a short sequence of actions through a policy module. So this is your policy module A. By the way, this thinking about policy module, if you're familiar with reinforcement learning, you can see that the languages are coming from there. That a policy is itself a function. It's a neural network, a policy network. Therefore, it's amiable to gradient descent. It can be trained to gradient descent. In other words, it goes to the key thing the author keeps mentioning, namely differentiable networks, end-to-end. So if you look at everything, you're familiar with autoencoders, you know that, of course, encoders are differentiable, policy networks are differentiable. And if you feed it into a prediction, and we saw that in iJPA, this, of course, is yet another differentiable. If you remember in IGFR, it was a VIT. It was a VIT there also. So that is again a differentiable network. So everything is differentiable in this. So now with this, let's look through model one thinking. The perception module estimates the state of the world as 0. So this is the perception. This is the latent representation. Of X, right? Which is your SX. X went in, SX came out. The actor directly computes the action or a short sequence of actions through a policy model. So this SX that came in, it went into this actors, a policy engine, a policy network. Policy network says, hey, let's go hit the ball. Let's hit the ball. Right? And then I suppose you get to the next stage, which is that you see the ball bounce. Now the ball bounces even better. And I suppose your reward, think of it as some, and I'll use the word reward, energy, it's a little bit interchangeable. It can be, oh, what utter fun. So you're happy now. The kid is happy seeing this. So that's it. That is it. So it says, the reactive process does not make use of the world model nor of the cost. The cost module computes the energy of the initial state. This is computed and stores the pair in a short-term memory. Optionally, it may also predict a next state. So these things which are slightly there, not quite darkened or mildly transparent, are optional. Next state using the world model, this and associated energy, so that the world model can be adjusted once the next observation resulting from the action becomes available. Right? So now you have, like you may have learned a little bit from that, which is your world model getting adjusted a little bit of what's happening. That is it. So this is model 1. This is purely reactive behavior. Okay? And model 2 is a little bit more complicated version of this. It says that, see, let's say that you take an input. So you're bouncing ball bouncing. And you encode it. When you encode it, this is your latent state, right? Latent representation. Now, what you do, you use the actor and its policy engine to predict a course of actions, a set of actions. It says, first do this. Let's go hit the ball to the left, and then we'll hit it to the right or whatever it is. Then that goes into a prediction engine, and it will tell you that if you hit the ball, you would go to this state. And if you do this action, you will go to this state. And then you hit the ball again, and you'll go to this state. I hope this looks very intuitive, isn't it? So imagine that you're dribbling with the ball, right? And as you dribble with the ball, you're pretty much going through a state of prediction. You're predicting, if I hit it down, this is where it will be. And if my next action is to dribble it a bit more, this is what it will be. Now, for each of these, you have a certain cost. I mean, he keeps using the word cost, energy, etc., fairly interchangeably. Energy functions associated with it. That is all fun. He's there. But now, let us say that there is a desirable outcome. Maybe you have to dribble it all the way and then, I suppose, shoot it into a goalpost. So the end result is, all of these put together, does it achieve the goal, right? One easy way to think of it is that ignore all the other outcomes or rewards for the outcome. Just focus on the last one. Did you finally get it to the goal? Now comes the part, if you couldn't get it to the goal, now what is the learning that you can do? You can always see, if you go on predicting the outcome, what you're saying is, if I'll hit it there, I'll hit there, I'll hit there, I'll hit there, and then I'll hit to the goal. But if your prediction says, no, if you do this, you're dribbling and taking it in the other way, you won't hit the goal. So then it is an undesirable state. What can you do? You can go and change your actions. You can, in other words, change inference time. You can actually do sort of a policy gradient to find a better set of action, a better actions, a series of actions that will give you better outcomes, isn't it? Without necessarily, So this is a point then he's making, and I'll read this part out. Model 2 perception action episode. The perception module estimates the state of the world, S0, which is that, oh, I see a ball. The actor proposes a sequence of actions, A0, A1, blah, blah, blah. So that is us dribbling the ball in this direction or that direction. The world model recursively predicts an estimate of the world state sequence. So it will keep predicting that if you dribble the ball, this is where you're going. Predicted state. The cost computes an energy for each predicted state in the sequence. So, for example, if you're dribbling the ball the wrong way, the energies will start increasing. Oops, you're making a mistake. It then sends the first action in the sequence. So what happens is that then comes the statement that is most important, I suppose. Computes the energy of each. And here's the part. Through an optimization or search procedure, the actor infers a sequence of action to minimize the total energy. Very abstract, but there's a lot here when we think of the bouncing ball. So in your mind, imagine that you replay many actions. If I dribble it and go from the left, or if I dribble and go from the right, if I dribble and go from this, you know what the outcomes will be at each stage. And therefore, what can you do? You can take one series of outcomes, actions you can predict. You can go on doing that. And then you can say, well, is it good? And you realize it's not good. So then what can you do? Because you have the policy, the actor has the policy network at its disposal. It can do what? It can do an optimization process at inference time to come up with a better set of actions that will lead to a better outcome. Right? Energy is optimizing on the energy is the same as looking for a better outcome of the set of actions. It can do that. It can keep on doing gradient descent in a very optimized way. It can search procedure to find better series of actions. And once it has found that, then it can say, all right, let's go and do the first action that is here. Let's go and do it on the world once I've found the best action. That is the crux of what he's trying to say. Are we together, guys? Huh? And we do that. If you, like human beings do that, you play on the basketball. You may not realize, but in your mind, your first thought may be, oh, I could go this way. And then you suddenly realize, no, that's not, I'm going to, here is that strong player that will intercept me. So then you say, okay, let's re-strategize. I can go this way. And that is what it is saying, that the actor has associated a network which can help it search and find the best set of actions to take at inference time. And therefore propose that into the world. And that is your more considered model 2 thinking. Right? It then sends the first action in the sequence to the effectors, which means that actuators. This is in effect an instance of the classical model predictive control with receding horizon planning. Well, if you're familiar with some of these AI models, this is what it is. Receding horizons means this, then that, then that, then that, and that, etc., etc. Since the cost and the models are differentiable, and again, this thing, he keeps mentioning this, since the cost and models are differentiable, the gradient-based methods can be used to search for optimal action sequence as in classical optimal theory. Since the total energy is additive over time, of course, these energies are, why are they additive? By definition, energies are scalars, numbers. Numbers are additive. Since the total energy is additive over time, dynamic programming can be used, particularly when the action spaces is small and discrete, which means that, you can remember that, okay, dynamic programming just means you have a memorization table. You can say, if I took action A, B, C, D, this is what happens. But maybe D is bad, let me remove it, but I still know what's the outcome of doing A and B and C. Right? So I can piecemeal change it without recalculating everything. That's all they're trying to say. Particularly when the action is small and discretized. Pairs of states computed by the encoder, predicted, etc., correspond to energies from the intrinsic cost and training the action. I hope this part is clear. And now comes the third big picture, which says that, once the machine is doing a lot of this, it should become second nature. What is model 2 thinking should gradually become model 1 thinking, or mode 1 thinking, or reactive thinking. So training reactive policy module from the results of Model 2 reasoning. Using Model 2 is onerous because it mobilizes. So as you can imagine, that long-term thinking is onerous. It takes a lot of effort. Think of yourself. Would you rather look at an ice cream, which is more or less reflexive, or would you rather solve a complicated problem in differential geometry, prove a theorem in differential geometry? When an ice cream is before you, it's so instinctive, Model 1 thinking, you just go grab it and eat it without thinking too much about it. Whereas proving a theorem, now you sit with a paper and pencil and you break your head over it. So the idea is that creating a reactive policy model from results of Model 2 reasoning. So how can you do that? How can you do at each point? And the point that he makes is that, see, and this is important, look at this. You have a policy engine. You create an outcome. So let us say that reactively, initially, this machine produced an outcome. It said that without doing long-term planning, it comes up with an action this. Then what happens? It leads to something, it leads to something, it leads to something. And then you realize that if you dribble your ball or you go with your ball in a basketball court in this particular way, well, you will get blocked. And so you then search for a better strategy to get to the goal or whatever. And then, by the way, I'm very bad with games. So whatever analogies I give, if you're rolling your eyes, that's perfectly legit. So, but let's say that you come up with a better course of actions. And now you know that that is a plausibly more winning strategy. So then what happens? Your first action changes, isn't it? You have come up with now a better action that you have learned. And so by looking at the gap, but now how do you learn? You always learn by looking at gradient of some error, some gap. The gap is between the initial action that you thought, action associated with S0, versus the action that you really should have taken, the real action that comes from your deep reasoning. What can you do? You can now train your reflexive behavior, the network policy gradient, to predict right off the bat the right action without going through long-term reasoning. You see that, right? That you can train a machine to get it right the first time, in effect, without going through the careful reasoning process. You can improve upon it. The reactive policy model can be improved. That's all it is. That's how you learn. From model to model 1 is a process of learning new skills. This is, I suppose, a reference to how we would do that. Reasoning as new energy minimization, I suppose. Now we'll talk about, there's a lot of technical they said it will be jargon free, but I suppose jargon free is in the eyes of the beholder. Right? There is a bit of jargon here, but for these great researchers, they look at this and say, oh, there's no jargon here. Now, what is this machine doing and how is it doing it? I'll skip over a lot of that. I notice that I've exhausted the time and we are at 9 o'clock. So folks, at this moment, we have a fork in the road. Should we continue for the next hour and a half or should we take it next week?
I think it would be good to take some questions and spill over into another session.
Yeah, let's do that because next time it gets a little bit more technical and we will go into some real architectures like this and this and this. And then you'll see the bridge over to the iJPA and things like that. So let's pause here, guys. At this moment, as you notice, this is all putting a position. Like this is how we could design an engine, keep it differentiable, end-to-end differentiable, make predictions, be non-generative, not use contrastive learning, even that's for a technical reason, and still get away with a machine that learns in a self-supervised manner. So as we delve more into this paper next week, I suppose, more will become. I suppose we'll get to more of it. So two questions, guys. First is, if you're going to pause here, are you interested in the rest of the paper, or have we done enough? And let's move on to another topic. Anyone who votes for us continuing and finishing the piece?
I would be one for continuing till the end, unless it is getting super esoteric. You know it by now, because it seemed to be headed into the system 1, system 2, which is good. And so going to the finality of it would be beneficial.
Any other comments, guys?
Yeah, for me too. I think it's wonderful actually to continue and finish it, but it also depends on everybody else's interest. I'll vote for yes.
Okay, so we have 2 votes for yes.
I vote yes as well.
Okay, all right. So that decides it, guys. Let's continue it next week. It's great things start with some in mathematics, especially, and I suppose in computer or in neural networks now. They start with a grand vision. People create programs. In math, for example, there's a tradition of creating a program, and then many mathematicians devote their lives to, quite a significant part of their effort for the next few years to helping realize that vision, that program. And
would you take? Sorry.
No, go ahead.
Sorry, would you take questions regarding the paper now?
Absolutely.
Do we have?
Let's do that.
So my question is a great paper actually. Multiple questions. So it looks like this is trying to tackle a multimodal situation actually. World model is not just text. It can be text too, but looks like it is also multimodal. And when they say non-generative, I get that. But this is, I mean, if you really want to make it implementable, then I think parallelization is also, have they implemented this ever?
Oh yes, iJEPA is very much a reality. iJEPA, VJEPA are realities.
They are realities, okay. And they are parallelized just like the generative models.
Yeah. So they are basically VIT. For example, iJEPA is a bunch of VITs, visual transformers. And of course, massive, as parallelizable as any transformer. It's just literally using VITs.
Okay, got it. And then one comment I wanted to make about the entropy function is it makes sense. Entropy loss functions are very similar. When I had attended that conference about physics-informed neural networks, they are very big into using actual PDEs and ODEs into actual loss functions, because then they have actual physics involved over there, and they can use that to minimize and get to the answer. So it doesn't need gobs and gobs of data. It just needs very little amount of data that you can train it. It looks to me that it was trying to figure out some similar entropy function. Ultimately, all the neural networks, what they end up interpolating is some polynomial, actually. We don't see it, but ultimately there's a polynomial behind it.
Right. See, the way I would put it is that these concepts like physics, etc., they are sort of the unstated subtext in the minds of these luminaries. If you look at for example, if you look at the speed, and starting with the very basics like the Hopfield network, and you see its close association with the Ising model, the foundation of it. The Ising model is the sort of like, for example, people say, right, that biologists, if they need to do an experiment, they'll do it on a Petri dish over a bacteria. So for physicists, the Ising model is sort of the basic toy model on which they reason. And if you look at Hopfield network and the Boltzmann machine and the restricted Boltzmann machine, the old classic methods, they all are there. Even if you look at the foundational paper, like for example, the start of this whole deep learning thing, Geoffrey Hinton's 2006 paper, it actually starts with aliens. And so
he did refer to Boltzmann machines. He said very close to be backpropagation, but didn't turn out to be. He claimed that in a talk in Ireland just 2 days ago, actually. I will chase.
Yeah, it's very actually. Please post that. Send that link to. Actually, I was just going to say post it to the Slack channel. Except that I've yet to create that Slack channel. Let me go do it. But if you could please email me that talk. I don't think I listened to that talk. I would like to. But see, guys, look at
Surely.
this.
It doesn't go deep into that, but he claims he did say that he almost came close to. He did invent Boltzmann machines, and he says my invention, and it came very close to be perfect back propagation,
Yes.
but it did not.
That is right. It is the one that predates. In fact, that's the way you used to train that. See, guys, you look at this temperature, right? It's very genuine. You increase the temperature, then just about all states are possible. You can see that in water, in steam, in things that the probability of if the T goes to infinity, for example, as the T increases, every number basically begins to be zero. So e to the zero means all states become probable. All of these intuitions, distillation, if you go back and read his Hinton's paper on distillation, he just adds this T there. I mean, he is a student learning, etc. All over the place, you will notice that these luminaries, they are thinking from a highly physics motivated perspective. And even today, there's a lot of belief in a sector of the community that we need to rethink deep learning from a physics perspective. And so you could look at it two ways. You can say that, hey, the yearning to have a physical or dynamic explanation or mechanistic explanation of machine learning and the learning process has led to a lot of great results in great neural networks. Positive way. Another way to say it is that people have been beating about the physics bush for a long time and nothing has come out. Right? I've heard that statement also. So it sort of depends upon how you look at it. I am biased towards a former perspective because I love math and physics.
By the way, a comment also just not really related to the discussion entirely. Daniel Kahneman, he passed away like 2 weeks ago, right? End of March. Yeah.
Oh.
I didn't know that.
Yeah. End of March, he passed away. I read his book. The analogy you gave about the farmer in the book, there's another one which is actually very apt for the Model 1, Model 2 thinking, for the way you're talking about it here. Is the example he gives in a corporation. They leave some candy, and each candy is $1, but you pay voluntarily. And so they put like 10 candies there, and then they found the collection was 10 candies gone, $2 collected in a large corporation with high salaries and all that. Right. The next time they put like a picture of a person with just the eye looking at the candy on the wall behind, and the collections went up. So that was like the system one thinking, basically just the eye there made people think somebody's looking, and then they put more dollars in the kitty.
Oh, I love that story. I love it. There is a story that I think goes to the poet Khalil Gibran, who once said that he just gives a story that I once stole my neighbor's melon or some fruit, watermelon or something like that, and I was enjoying it, but then I realized my neighbor was looking at me, and that's when I felt guilty. When you see watching eyes.
Interesting. Very good. There was an interesting referral I got recently while listening to one of these YouTube talks. Rick Sutton. And Rick Sutton is on record saying it's all about compute. It's not about human intelligence anymore. It's not about do not get into. Essentially, that's what I could distill out of that, saying all this hierarchical and this and that and whatnot.
I mean, it's all about compute. Like, say more.
Yeah. I'll try to find that link and send it across. But essentially, that's what Rick Sutton was saying, that compute is finally going to win. Do not try to get human intelligence into that, because your thinking might be different than somebody else's thinking. We as a human race have written down everything that we have. So let compute figure it out. Because if you just go by one person's learning, then you might be overfitting to that. So let compute figure out all the rules. Just like what you mentioned in the other one, the bootcamp, attention is all you. What the entire system is learned by just throwing gobs and gobs of data at it. So that was an interesting. It kind of made sense, but I understand the hierarchical model too. So don't know which way I'm swaying at this moment.
There is a parallel I find. I suppose I should, this is a wider audience and I hope it doesn't come off. There was in India, one of the oldest philosophers in the analytical tradition, as in what the way Western philosophy is crafted in, the analytical philosophy of Bertrand Russell and Wittgenstein and things like that. If you look at it in Whitehead, in that tradition, there was a philosopher called Kapil. He is supposed to be the founder of a school of thought in India called the Sankhya philosophy. Now, to the best of my knowledge, he was the first to expound the concept that what in this paper I found as the world models. It says that knowledge is the ability to categorize sense perceptions and fit them to, I suppose, what this paper would call a world model, but be able to categorize and say this is a cow, but a cow is sort of a collection of attributes, behaviors and attributes that makes up the cowness of a cow, and so on and so forth. So he went quite a bit into it, and he, like, when you read through the original thing, you see a huge parallel between for example, machines trying to classify things and therefore saying it's a cow, and learning. So, for example, a CNN, why does it learn that it's a cow? It creates so many feature maps internally, internal representations. And the way I look at it is, I see resonance of that, because these abstract feature maps are perhaps those elemental or those atomic attributes that come together to make the cowness of the cow. So there's a lot. I suppose humanity has been thinking these thoughts over and over and over again for thousands of years.
But there is also this thing that Jan LeCun keeps on saying, that the little child learns about, there is something innate in human beings, because we learn about gravity very early on. The child learns about gravity very, very early, even before it has learned about, its dictionary has not even improved or become bigger, but learns about gravity by looking at objects, seeing things. So somehow that encoding is being passed on through, and that is not something we can learn very easily. So, and there are no words, tons of words written about gravity, actually, right? I mean, yes, there is something written that, when an object moves a little bit on a sloping desk, it's going to fall down. But that is something we very innately know it by just looking at things. So how will these, not LLMs, but these systems, models, foundational models, frontier models, learn about physics? Is it like a combination of Wolfram and LLMs?
Right. Yeah, we are in a Swiss cheese at this moment. I suppose this is the age of cognitive science, with AI, with neuroscience, with psychology, with all of this. The new frontier we are exploring is the thinking itself. I'm trying to simulate thinking and learning.
Yeah, in the computer vision community, I think the idea that you will actually, like the example you gave us about the ball. So a kid who learning about the ball is not just using vision, is actually using touch. And it's not like getting training data, they're actually interacting with the training data.
Right.
They're taking the ball, feeling the ball, moving the ball around, looking at it from different angles. They put it on a table, it falls, they learn gravity perhaps intrinsically. And so they're interacting with the training data and multimodal, like tactile. Those are elements, and smell as well. Those are elements which are yet to come into the vocabulary of what we consider deep learning right now, I guess. I don't know. So that those things need to be in place for it to be equivalent to a child's learning capacity. Just vision is not, just text is not enough, basically. That's the idea, at least.
Yes. No, absolutely. This is, and you see this happening, right? At this moment, what do? We put tons of data. It's just forward pass, backward pass.
Yeah.
But whereas a child playing with and learning with a ball, bouncing ball, is a very, very iterative process. It's more like,
yeah, you're actually interacting with the training data. The training data is not a fixed input. You're actually modifying the training data, like what we do in computer vision, right? We do transformations of the image. For the
right.
child, it's not like right now transformations is part of the training data, but here the thing which is getting trained is the one which is actually transforming the data. Like the child is moving the ball around to figure out what the ball is. And so it's an interesting.
Yeah, so this is just extending on that, Asif. So today's these LLMs have been pre-trained. Are they learning too at the same time based on all they are, right? Based on the questions and answers, all the things they are learning too, but they are pre-trained. So I'm trying to understand, because this model that Jan LeCun and gang mentioned, they are learning all the time, actually. I mean, I don't know whether there's a pre-training phase and then there is a...
See, energy-based model. So two aspects here. Learning has a very strong definition, strict definition in machine learning. It is saying minimizing a loss function. Right? The process of minimizing a loss function is the process of gradient descent and back, all of them. Now comes the thing, energy-based models have this virtue that it is not just finding the optimal point of a loss function. It is like at inference time, you're finding what is the best course of action. And in a way, your policy network helps you do that. Things like that, action policy network helps you do that. Collectively discover and optimize on that. So in that sense, it is obviously discovering the best action. People don't use the word learning at inference time. People have a very strict dichotomy between learning phase and the inference phase at this moment. It is certainly true that should that be there, should we not have continual learning in the model while we are doing inferencing? Practical realities dictate that you don't want to do that because people can hijack your system and teach it all sorts of things that you don't want it to do, and then you'll be in trouble. So people train the model offline, then they bring it online, and then it is used for inference. There is such a thing as online learning, or online learning literally is that as data comes in, but it is labeled data, and the machine continually keeps learning from that and from the mistakes it's making. But it is not as prevalent.
Great session, Asif. Enjoyed it thoroughly. Loved it.
Thank you. Yeah, go ahead.
Yeah, it's very good.
I was just about to say, yeah, I don't think I've ever seen mine.
Online learning in production. Yes. Yeah, it's very, it is done with a little streaming data. Remember that when the big data, streaming big data movement was there were entire books written on sort of literally machine learning on streaming data. Some of these algorithms are pretty good, but they are certainly not in widespread use. All right, folks. So if that is that.
Yeah. Thanks, Asif. Great session.
You're welcome. Thank you, guys. Thank you for being here and being part of our Support Vectors learning community. We look forward to seeing you again next week, and let's finish this one.
Thank you very much, Asif.
Good night.
Good night.
Thanks for all the great work and helping the community.
Yeah.
Thanks.
Thank you, Asif.
Thank you, Mike. Good night.